In the vastness of space, there exists a silent mystery. A presence that cannot be seen, yet reveals itself through the structure of everything that exists. It is neither star nor dust, neither gas nor radiation. It is the hidden backbone of the cosmos, dark matter. For decades, scientists have tried to uncover what dark matter is. They know it exerts gravity. They know it shapes galaxies. They know it dominates the mass of the universe. And yet, despite all this knowledge, they have never directly seen it. Dark matter is invisible. It does not emit light. It does not absorb light. It does not reflect light. The instruments of astronomy, telescopes that capture every wavelength, from radio to gamma rays, all fail to detect it. Still, the evidence of dark matter surrounds us everywhere. Galaxies spin faster than they should, held together by unseen mass. Clusters of galaxies bend light in ways only extra gravity could explain. The pattern of the cosmic microwave background, the afterglow of the Big Bang, reveals ripples that can only be described if something more than visible matter was present. These observations lead to one conclusion: most of the matter in the universe is not the kind we can see. Not the atoms that make up stars, planets, or even us. Ordinary matter, also called baryonic matter, accounts for less than 5% of the universe. Dark matter makes up nearly 27%. The rest, the largest share, is dark energy, a different mystery entirely. But dark matter is older than galaxies, older than stars. It formed in the earliest moments after the Big Bang, influencing everything that followed. Its gravitational pull guided the formation of galaxies and clusters. It sculpted the large-scale structure of the universe, a cosmic web stretching across billions of light years. Without dark matter, the universe as we know it could not exist. And yet, its true nature remains hidden. The story of dark matter begins with an observation and a question. In the early 20th century, astronomers began to measure how stars move within galaxies. They expected that stars near the edges of galaxies would orbit more slowly than those near the center, just as planets in our solar system move more slowly the farther they are from the sun. But when the data came in, something didn't add up. The stars were moving too fast. They orbited at nearly the same speed, regardless of distance from the galactic center. According to Newtonian mechanics, this was impossible, unless there was more mass than they could see. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive group of galaxies. He noticed the galaxies within it were moving so quickly that the cluster should have flown apart, unless some invisible substance was holding it together. He called this missing mass Dunkel Materie, dark matter. At the time, few took Zwicky's claims seriously. The technology to test his theory didn't yet exist, and the idea of invisible matter seemed speculative. But as decades passed, more evidence began to emerge. In the 1970s, American astronomer Vera Rubin measured the rotation curves of spiral galaxies with unprecedented precision. Her observations confirmed that stars at the outer edges moved just as fast as those near the center. The visible matter, stars, gas, dust, could not account for the necessary gravitational pull. The conclusion was inescapable. Something unseen, something massive, surrounded each galaxy in a vast halo. That was the turning point. Dark matter was no longer a theoretical concept. It was a measurable phenomenon. Every galaxy, including our Milky Way, is believed to be embedded in a halo of dark matter, an enormous, roughly spherical region of invisible mass that extends far beyond the visible stars. This halo dictates how the galaxy rotates, how it interacts with others, and how it evolves over time. If dark matter did not exist, galaxies would tear themselves apart. The gravitational force of their visible matter alone isn't enough to keep them bound at the observed speeds. Dark matter's unseen mass provides the necessary glue. But what exactly is this invisible mass made of? This question remains one of the most profound mysteries in modern physics. Scientists have proposed various possibilities. Perhaps dark matter is composed of undiscovered particles, weakly interacting massive particles, or WIMPs for short. Or maybe it consists of lighter particles called axions. Some theories suggest it could even be a mix of several unknown forms of matter. None of these particles have yet been detected. Despite decades of research and countless experiments, dark matter continues to evade every attempt to observe it directly. Even if we cannot see dark matter, we can map where it is. Astronomers do this by observing how its gravity affects the motion of stars and galaxies, and how it bends light, a phenomenon known as gravitational lensing. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies, its path curves. The greater the mass, the stronger the bending. By studying this distortion, scientists can infer the amount and distribution of dark matter in that region of space. These gravitational lensing maps reveal vast structures that resemble a cosmic web, filaments of dark matter stretching across the universe, connecting galaxies and clusters like threads of an invisible network. This large-scale structure supports the idea that dark matter played a key role in the universe's evolution. After the Big Bang, ordinary matter was too hot and energetic to clump together. Dark matter, unaffected by radiation, began to collapse under its own gravity, forming dense regions, the seeds of future galaxies. As the universe cooled, baryonic matter fell into these dark matter wells, igniting stars and creating the galaxies we see today. In this way, dark matter acted as the scaffolding of the cosmos, the invisible framework upon which the visible universe was built. Despite its critical role, the nature of dark matter remains elusive. It doesn't interact through the electromagnetic force, meaning it doesn't emit or absorb light. It also seems not to interact through the strong nuclear force that binds atomic nuclei. The only forces it appears to obey are gravity and, possibly, the weak nuclear force. That is why direct detection is so difficult. Billions of dark matter particles may pass through your body every second, yet they leave no trace. They pass through the earth, through walls, through detectors, as though nothing were there. To detect something that barely interacts requires immense sensitivity and extraordinary patience. All around the world, scientists have built elaborate detectors to search for dark matter. Many are located deep underground, shielded from cosmic rays and background radiation. These detectors are filled with ultra-pure materials, such as liquid xenon or germanium crystals, that can record the faintest of interactions. If a dark matter particle were to collide with an atomic nucleus, the detector might record a minuscule flash of light or a tiny vibration. So far, no experiment has definitively confirmed such an event. But each test helps narrow down the range of possible properties dark matter could have. The search continues, expanding from underground detectors to particle accelerators and space-based telescopes. Physicists hope that by studying high-energy collisions or cosmic rays, they may uncover indirect signs of dark matter interactions. Even null results, experiments that detect nothing, are valuable. They rule out certain models, helping scientists refine their understanding of what dark matter might be. To understand dark matter is to understand the universe itself. It influences cosmic expansion, galactic formation, and the behavior of entire clusters of galaxies. Its presence is written into the very geometry of space-time. Yet, dark matter is more than a cosmic curiosity. It challenges our understanding of physics. It suggests that the standard model of particle physics, one of the most successful theories ever devised, is incomplete. Dark matter may hold the key to physics beyond the standard model, to new particles, new forces, and new laws of nature. It may even lead us to insights about dark energy and the ultimate fate of the universe. As we look into the night sky, everything we see, the stars, the galaxies, the glowing nebulae, represents only a small fraction of what truly exists. The rest is hidden. The luminous universe is but a thin film floating on a vast ocean of the unseen. The deeper scientists peer into that darkness, the more questions arise. What if dark matter is not made of particles at all, but something more exotic, like primordial black holes or hidden dimensions of space? Could it be related to other fundamental mysteries, such as neutrino mass or quantum gravity? Each possibility opens a new path of inquiry, and each unanswered question reminds us how much we still have to learn. The universe is not just larger than we imagine. It is stranger, subtler, and more mysterious than we can yet comprehend. The mystery of dark matter begins not with what we can see, but with what we cannot explain. Across the cosmos, from the smallest dwarf galaxies to the largest clusters, the laws of motion reveal a strange imbalance. Stars orbit too quickly, galaxies cling together too tightly, and the cosmic web stretches far too far. The visible universe is not enough to account for the gravity that holds it all in place. Astronomers first began to notice this imbalance in the early 20th century. They had developed the tools to measure the velocities of stars and galaxies, and they expected those motions to follow the rules of Newtonian gravity, rules that had governed celestial mechanics for centuries. A star orbiting the center of a galaxy, much like a planet orbiting the sun, should move more slowly the farther it is from the center. But observations told a different story. When scientists measured the speeds of stars at the outer edges of galaxies, they found that those stars moved just as fast as the ones near the center. The rotation curves, graphs showing how velocity changes with distance, were flat instead of declining. If only the visible stars and gas were providing the gravitational pull, the outer stars should have drifted away long ago. The galaxies should not hold together at all. Something invisible was exerting an additional force, an unseen mass that made the galaxies whole. This was the first undeniable sign of dark matter's influence. The galaxies were surrounded by halos of invisible mass. Without that extra material, the stars would have scattered into intergalactic space. Over time, astronomers began to see the same pattern everywhere they looked. Dwarf galaxies, elliptical galaxies, massive spirals, all showed the same flat rotation curves. The only logical explanation was that a vast amount of unseen matter surrounded and permeated them all. Further evidence emerged from galaxy clusters, those immense gatherings of hundreds or thousands of galaxies bound together by gravity. In the 1930s, Fritz Zwicky measured the motions of galaxies within the Coma cluster. They moved so rapidly that the cluster should have flown apart, unless some invisible mass was providing the gravitational glue. Zwicky estimated that the visible matter, the stars and gas in the galaxies, made up only a small fraction of the total. He concluded that the rest must be dark matter. At first, his claim was controversial. Many astronomers dismissed it as speculation or error. But as measurements improved, the discrepancy persisted. The more data scientists collected, the clearer it became that something unseen was dominating the universe's mass. Another kind of evidence came from the way light travels through space. According to Einstein's general theory of relativity, massive objects curve the fabric of space-time, bending the path of light that passes nearby. This effect, known as gravitational lensing, allows scientists to measure the mass of cosmic structures, not by what they emit, but by how they distort the light from more distant sources. When astronomers observed galaxy clusters using this technique, they found that the bending of light was far stronger than could be explained by the visible matter alone. The gravitational lensing revealed far more mass than telescopes could see. The clusters were embedded in enormous halos of dark matter, hundreds of times more massive than the galaxies themselves. One of the most striking examples came from a collision between two galaxy clusters known as the Bullet Cluster. When the two clusters collided, their clouds of hot gas, which contain most of the visible mass, slammed into each other and slowed down, emitting X-rays in the process. But the gravitational lensing map told a different story. The majority of the mass passed straight through the collision, almost unaffected. The invisible matter had continued on its way, separating from the gas. This event provided some of the clearest evidence that dark matter is a distinct form of matter, not just an illusion created by modified gravity. It showed that dark matter does not interact strongly with normal matter or with itself, except through gravity. It behaves like a vast, invisible sea that flows through the universe, shaping everything but remaining untouchable. Cosmic microwave background radiation, the faint afterglow of the Big Bang, provides another window into the nature of dark matter. This radiation, discovered in 1965, fills the universe uniformly, but with tiny fluctuations in temperature and density. Those fluctuations record the conditions of the early universe, just 380,000 years after its birth. When scientists map these patterns, they can deduce how much matter existed at that time and how it was distributed. The results reveal that ordinary matter alone could not produce the structures we see today. If only baryonic matter had existed, galaxies and clusters would not have had time to form before the universe expanded too much. Dark matter, unaffected by radiation, began to clump earlier, creating gravitational wells that drew normal matter in. The detailed measurements of the cosmic microwave background, especially from satellites like COBE, WMAP, and Planck, show that dark matter must make up about 5 times as much mass as ordinary matter. The shapes and scales of the temperature fluctuations match the predictions of models that include dark matter perfectly. Without it, the observed universe would look drastically different. The large-scale structure of the universe, the web of galaxies and voids, also testifies to dark matter's role. When cosmologists simulate the formation of the universe using only the laws of physics and the presence of dark matter, they reproduce the observed patterns almost exactly. In these simulations, dark matter collapses under gravity into filaments and nodes, forming a cosmic web. Galaxies form along these filaments, where dark matter's gravity is strongest. If the simulations exclude dark matter, the result is completely different. The universe fails to form the rich, complex structures we see today. Galaxies become rare and isolated, and the cosmic web disappears. Only by including dark matter can the universe come to resemble the one we observe. Even the internal structure of galaxies bears the imprint of dark matter. In spiral galaxies, the visible disk of stars and gas is only a small fraction of the total mass. The dark matter halo extends far beyond, often 10 times wider than the visible portion. This halo determines the way the galaxy rotates, evolves, and interacts with its neighbors. In elliptical galaxies, dark matter shapes the velocity distribution of stars, influencing the galaxy's stability and long-term behavior. Clusters of galaxies provide another level of confirmation. The hot gas within them, observable in X-rays, makes up most of the visible mass, but it is still not enough to account for the gravitational binding energy needed to keep the cluster intact. When astronomers measure the total mass through gravitational lensing or through the motions of galaxies within the cluster, they consistently find that about 85% of the mass is invisible. Even within our own Milky Way, the evidence is unmistakable. The Sun orbits the galactic center at a speed of about 220 kilometers per second, far faster than it would if only visible matter were present. The rotation curve of the Milky Way remains flat far beyond the region where most of the stars lie, indicating a vast halo of dark matter enveloping our galaxy. Over the decades, every new measurement has reinforced the same conclusion. Whether through galaxy rotation curves, lensing, or cosmic microwave background data, the universe is dominated by a form of matter that we cannot see. Some scientists have proposed alternatives, modifications to the laws of gravity that might explain these phenomena without invoking unseen matter. These theories, such as modified Newtonian dynamics, MOND, attempt to change the way gravity behaves at very low accelerations. While they can explain some galactic rotation curves, they struggle to match the evidence from galaxy clusters, gravitational lensing, and the cosmic microwave background simultaneously. The simplest and most consistent explanation remains dark matter. Although the gravitational effects of dark matter are clear, its composition remains one of the deepest questions in modern science. The leading hypothesis is that dark matter consists of particles, possibly WIMPs, weakly interacting massive particles. These hypothetical particles would have mass but would interact only through gravity and the weak nuclear force, making them extremely difficult to detect. Other possibilities include lighter particles called axions, sterile neutrinos, or even entirely new classes of particles that have yet to be imagined. Each possibility leaves a subtle fingerprint on the universe, and scientists use every available observation to look for clues. Astrophysicists have also looked for signs that dark matter might annihilate or decay, producing gamma rays or other detectable signals. Telescopes such as the Fermi Gamma Ray Space Telescope have searched the centers of galaxies and dwarf galaxies for these emissions. So far, no definitive signal has been found, but the search continues. Some experiments look for hints of dark matter's influence on cosmic rays, the high-energy particles that travel through space. If dark matter particles annihilate, they might produce excess positrons or antiprotons that could be detected by instruments aboard satellites or the International Space Station. Again, no clear signal has emerged, but each experiment helps refine our understanding. Gravitational lensing surveys have mapped dark matter on cosmic scales, revealing how it clusters and evolves. Weak lensing studies, which measure subtle distortions in the shapes of millions of background galaxies, have created detailed maps of the dark matter distribution across the universe. These maps show how dark matter forms a vast skeleton of cosmic structure, connecting clusters and voids in a web-like pattern. This cosmic web is not static. Over billions of years, dark matter has continued to collapse under gravity, pulling ordinary matter with it. The galaxies we see today sit within these dark matter filaments, like bright islands in an invisible sea. The consistency of all these observations, from individual galaxies to the largest structures in the universe, forms an overwhelming body of evidence. Every line of data points to the same conclusion: dark matter is real, and it dominates the cosmic landscape. The challenge now lies not in proving that dark matter exists, but in determining what it is. Its gravitational fingerprints are everywhere, but the particles themselves remain hidden. Scientists continue to build more sensitive detectors, refine their models, and look deeper into the cosmos. As they do, they are also testing the limits of known physics. The discovery of dark matter's true nature would extend our understanding of the universe to new realms, revealing a hidden layer of reality that has shaped everything from the beginning of time. The story of dark matter is not just a story of what we cannot see. It is a story of how we have learned to read the universe's invisible handwriting, the subtle imprints of gravity, motion, and light that reveal the presence of something profound and unseen. Even though the evidence for dark matter is overwhelming, the mystery remains unsolved. We can trace its effects, but we cannot yet describe its substance. We can map its distribution, but we cannot yet name its particles. It is the silent majority of the cosmos, holding galaxies together while eluding every instrument designed to find it. As we continue to study it, dark matter challenges our understanding of nature's most fundamental laws. It invites us to question what matter truly is, and whether our theories are complete. It reminds us that the universe is not made only of what shines, but of what hides in the dark. And in that darkness, the evidence is clear. There is far more to the universe than meets the eye. The universe, in all its visible beauty, is only the surface of a far greater structure. Beneath the galaxies and stars, beneath every glowing nebula and cluster, lies an invisible framework. This structure is woven from something that does not shine, does not interact with light, and yet governs the arrangement of everything that does. It is the hidden architecture of the cosmos, the great cosmic web sculpted by dark matter. When we look out into the night sky, we see the luminous part of the universe, stars burning across spiral arms, galaxies drifting through space, clusters bound together by gravity. But what we see is only a small portion of a much larger whole. The true shape of the cosmos can only be revealed through careful observation and simulation, and those reveal a universe built upon filaments of dark matter stretching across billions of light years. The story of how this invisible web came to be begins shortly after the Big Bang, when the universe was still young, less than a few 100,000 years old. At that time, matter and radiation were tightly coupled. Photons constantly interacted with electrons, creating a dense, opaque plasma. The universe glowed with energy but could not yet form structures. Tiny fluctuations in density existed, left over from quantum variations in the earliest moments of inflation, but they were small, 1 part in 100,000. Ordinary matter, because it was charged and interacted with radiation, could not collapse under gravity during this early epoch. Every attempt at clumping was resisted by radiation pressure. But dark matter was different. It did not interact with light. It was invisible to radiation, free to respond only to gravity. As the universe expanded and cooled, dark matter began to drift together, pulled by its own gravity into regions of slightly higher density. These small differences grew over time, creating invisible wells, concentrations of dark matter that deepened as they attracted more material. These would become the seeds of galaxies and clusters. Meanwhile, ordinary matter remained coupled to radiation, unable to follow dark matter into these gravitational wells. It wasn't until about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms, that the radiation decoupled and the cosmos became transparent. The light from that moment still travels through space today as the cosmic microwave background. Once free from radiation pressure, ordinary matter began to fall into the dark matter wells that had already formed. There, it compressed, heated, and eventually ignited the first stars. The gravitational blueprint laid down by dark matter became the skeleton upon which all luminous structures grew. As time passed, these regions of dark matter merged and connected, forming a network that spanned the universe, an intricate web of filaments and nodes surrounding vast empty voids. In the densest regions where filaments intersected, galaxies and clusters of galaxies formed. Between them stretched immense spaces, nearly empty except for the faint traces of dark matter that connect them. This cosmic web is not random. Its structure follows the laws of gravity and the distribution of dark matter from the early universe. Simulations of cosmic evolution, such as the Millennium Simulation and Illustris, show that when dark matter is included in the equations, the resulting structure closely matches what astronomers observe through large-scale galaxy surveys. In these simulations, dark matter particles move and cluster over billions of years, forming long filaments that snake through space. Ordinary matter, following the gravitational pull of these filaments, gathers in the same regions, forming galaxies and stars. Without dark matter, these simulations fail to produce the universe we see. The visible cosmos is a mere reflection of the dark scaffolding beneath it. Observational evidence for this structure comes from the large-scale distribution of galaxies. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies across vast volumes of space, revealing patterns that resemble a web. Galaxies cluster along filaments, leaving enormous voids tens of millions of light years across. The shape and scale of these structures align almost perfectly with predictions made by dark matter cosmology. The web itself is shaped by the competition between gravity and cosmic expansion. Dark matter's gravity pulls matter together, while the expansion of space pushes it apart. In regions where the density of dark matter is slightly higher than average, gravity wins, drawing in surrounding material. These regions grow denser over time, forming filaments and halos. In under-dense regions, expansion dominates, creating the great cosmic voids. As billions of years pass, the web evolves. Smaller dark matter halos merge into larger ones, just as small galaxies merge into larger galaxies. Clusters form at the nodes of the web, where filaments intersect. Within these clusters, hundreds or even thousands of galaxies orbit within a single massive dark matter halo. At smaller scales, dark matter continues to shape the evolution of individual galaxies. Each galaxy resides within its own halo, and the properties of that halo determine much of what happens inside. The density and distribution of dark matter influence the rotation speed, the stability of the galactic disk, and the rate at which gas can cool and form stars. Even the dark matter halos themselves have structure. They are not uniform spheres but complex, dynamic systems. Their density peaks at the center and falls off toward the edges, following a pattern known as the Navarro-Frank-White profile. Within these halos, smaller subhalos orbit like satellites, remnants of smaller systems that were absorbed during cosmic evolution. These subhalos are thought to host dwarf galaxies, small, faint systems that orbit larger galaxies like the Milky Way. The number and distribution of these dwarfs provide important clues about the nature of dark matter. Observations show that there are fewer dwarf galaxies than predicted by some dark matter models, leading scientists to refine their understanding of how dark matter behaves on small scales. Dark matter's influence extends beyond the visible boundaries of galaxies. In galaxy clusters, the dark matter halos of individual galaxies overlap, forming massive, interconnected regions of gravitational potential. These halos bind the cluster together, governing the motions of galaxies within it and trapping the hot gas that emits X-rays. The presence of dark matter also explains why clusters act as powerful gravitational lenses. When light from distant galaxies passes through a cluster, the mass of dark matter distorts it, magnifying and stretching the images of background galaxies. By studying these distortions, astronomers can map the dark matter distribution directly. The resulting maps reveal dense concentrations of dark matter in the cluster cores, consistent with theoretical predictions. These observations are not just beautiful visual confirmations, they are precise measurements that quantify dark matter's role in cosmic evolution. By comparing lensing maps, X-ray data, and galaxy motions, scientists can determine the ratio of dark to visible matter and test how it changes over time. On even larger scales, dark matter influences how galaxies move relative to one another. The gravitational pull of the dark matter web causes galaxies to stream along filaments toward denser regions. This motion, known as peculiar velocity, creates subtle distortions in redshift surveys, providing another indirect measurement of dark matter's distribution. The cosmic web also affects how light travels through space. As light from distant quasars and galaxies passes through filaments of dark matter and gas, it is absorbed at specific wavelengths, creating what is known as the Lyman alpha forest in the spectra of quasars. This forest of absorption lines encodes information about the density and temperature of intergalactic gas, which in turn reflects the underlying distribution of dark matter. By studying the Lyman alpha forest across many lines of sight, astronomers can reconstruct the three-dimensional structure of the cosmic web. These reconstructions match the patterns seen in simulations, confirming that dark matter drives the formation of cosmic structure from the smallest to the largest scales. The balance between dark matter and dark energy determines how the cosmic web evolves. In the early universe, dark matter's gravity dominated, pulling matter together and building structure. In more recent epochs, dark energy, the mysterious force driving cosmic acceleration, began to counteract gravity, slowing the growth of structure. As the universe continues to expand, the filaments of the cosmic web will stretch and thin. Over time, the connections between clusters will weaken, and the universe will grow more isolated. But for now, the dark matter web continues to shape the cosmos. It provides the framework within which galaxies form and evolve. Its gravity dictates the motions of stars and the distribution of gas. It is the silent architect of the universe, unseen but omnipresent. When we observe the night sky, every galaxy we see is a bright node in this invisible network. The light from those galaxies travels through filaments of dark matter, distorted by their gravity. The structure we see across billions of light years is a direct reflection of dark matter's unseen hand. The Milky Way itself is one of countless galaxies embedded in this web. It lies along a filament that connects our local group of galaxies to larger structures like the Virgo supercluster and the Laniakea supercluster. All of these vast systems trace the same invisible framework of dark matter that spans the observable universe. In computer simulations, when researchers visualize dark matter, it appears as a faint, glowing lattice, a three-dimensional network of filaments and nodes. Within each node lies a cluster of galaxies. Along each filament, smaller halos mark the locations of galaxies and groups. The spaces between these structures are nearly empty, vast cosmic voids where the density of matter is extremely low. This pattern is remarkably consistent across different scales. From tens of millions to billions of light years, the structure of the universe retains the same general form. The web-like arrangement arises naturally from the physics of dark matter and the expansion of space. If we could somehow remove all the dark matter from the universe, the cosmic web would vanish. Galaxies would drift apart, clusters would disperse, and the large-scale structure would collapse. Dark matter's gravity is the glue that holds the universe together. It is the reason that galaxies exist in groups, clusters, and superclusters rather than floating alone in an empty void. Understanding this cosmic web is not just about mapping the universe's structure, it is also a way to test fundamental physics. The way dark matter clusters and evolves depends on its properties, its mass, its interactions, and whether it moves quickly or slowly compared to the speed of light. If dark matter is cold, meaning it moves slowly, it clumps efficiently and produces small-scale structures such as dwarf galaxies. If it were warm or hot, moving faster, it would smooth out small fluctuations, suppressing the formation of smaller galaxies. Observations of the cosmic web favor the cold dark matter model, which predicts the right amount of structure across different scales. Even small deviations from this model could reveal new physics. That is why cosmologists study the distribution of galaxies, the shapes of clusters, and the weak lensing patterns of the cosmic web with such precision. Each observation is a window into the behavior of dark matter, helping to constrain its possible forms. The cosmic web also influences the future of the universe. As dark energy continues to accelerate cosmic expansion, galaxies beyond our local region will drift away, moving faster than light can reach us. Over billions of years, the web will fade from view, leaving isolated islands of galaxies surrounded by darkness. Yet the dark matter that forms the web will remain, continuing to shape its local environment long after the visible connections have vanished. In the distant future, long after the stars have burned out and galaxies have dimmed, the web of dark matter will still define the gravitational landscape of the cosmos. It will persist as the underlying structure of everything, silent and invisible, holding the memory of a universe that once shone brightly. Our understanding of this cosmic web has come from a combination of observation, theory, and simulation. Every new map, every new survey, adds detail to the picture. Yet even as the image becomes clearer, the substance remains a mystery. We can trace where dark matter is, but not what it is made of. The cosmic web, in all its grandeur, is both a triumph of modern cosmology and a reminder of how much remains unknown. It shows us that the universe is connected in ways we can scarcely imagine. Vast networks of matter linking galaxies across unimaginable distances, all governed by a form of matter we cannot see or touch. In the darkness between galaxies, in the invisible filaments that bind them together, lies the true shape of the universe. Every cluster, every star, every planet exists because of that hidden structure. Dark matter has been the silent sculptor of cosmic history, shaping the universe from its earliest moments to the vast expanse we see today. Though invisible, it has left its mark on everything. And as we continue to study its patterns, we move closer to understanding the profound order hidden within the darkness. The search for dark matter is one of the greatest scientific pursuits of our time. Across the planet and deep beneath it, in space and in laboratories, scientists have dedicated decades to uncovering what this mysterious substance truly is. We know it exists because of its gravitational pull, yet no telescope has ever seen it. No particle detector has confirmed it. It is the invisible majority of the cosmos, and finding it means confronting the limits of human knowledge. The story of this search begins with the realization that ordinary matter, the matter that makes up everything familiar, is not enough to explain the universe we observe. The standard model of particle physics, one of the most successful theories ever developed, describes all known particles and forces, from electrons and quarks to photons and neutrinos. It has been tested to extraordinary precision, but it does not include any particle that could account for dark matter. This absence has driven physicists to search for something beyond the standard model, a new form of matter that interacts very weakly with ordinary particles, yet has mass and obeys gravity. Such a particle would be invisible, but its presence could explain the missing mass in galaxies, clusters, and the cosmic web. One of the most widely considered candidates for dark matter is known as the weakly interacting massive particle, or WIMP. These hypothetical particles would have masses ranging from tens to thousands of times that of a proton and would interact only through gravity and the weak nuclear force. If WIMPs exist, they could have been produced in large numbers during the early universe, left over as a relic population from the hot plasma that followed the Big Bang. The WIMP miracle is that such particles would naturally produce the correct amount of dark matter we observe today, without fine-tuning. This elegant coincidence made WIMPs one of the leading candidates for decades. To find them, scientists built some of the most sensitive detectors ever constructed. Massive instruments designed to sense the faintest possible interactions between a dark matter particle and ordinary matter. These experiments are usually placed deep underground, inside mountains or abandoned mines, to shield them from cosmic rays and background radiation. One such experiment is the Xenon project, located beneath Italy's Gran Sasso mountain. It consists of a large tank filled with liquid xenon, surrounded by layers of shielding. When a particle passes through, it can collide with a xenon atom, producing a tiny flash of light and a small electrical signal. The system is designed to detect these rare events with extreme precision. If a WIMP were to pass through the detector and interact with a xenon nucleus, it would create a distinct signature. Scientists would be able to separate this signal from background noise, confirming the presence of dark matter. So far, however, experiments like Xenon, Lux, and Panda X have not detected any confirmed events. Each null result helps narrow down the possible properties of dark matter, its mass, its interaction strength, and its behavior. Another class of detectors, such as Super-CDMS and Edelweiss, uses cryogenic crystals cooled to near absolute zero. These experiments look for minute vibrations in the crystal lattice when a dark matter particle collides with an atom. Again, no clear signal has been found, but the sensitivity continues to improve. In parallel, physicists are also searching for indirect evidence of dark matter through its potential annihilation or decay. If dark matter particles can annihilate each other when they meet, they would produce high-energy particles such as gamma rays, positrons, or neutrinos. These could be detected by space telescopes or ground-based observatories. The Fermi Gamma Ray Space Telescope has surveyed the sky for excess gamma rays that could come from dark matter annihilation, especially in regions with high dark matter density, like the center of the Milky Way or nearby dwarf galaxies. There have been hints of possible signals, but none have been confirmed as definitive evidence. Neutrino observatories, like IceCube at the South Pole, also search for dark matter signatures. If dark matter particles accumulate in massive objects such as the Sun or Earth, they could annihilate and produce neutrinos that escape and reach detectors. So far, no clear pattern has emerged, but the data continues to improve. At the same time, the world's most powerful particle accelerator, the Large Hadron Collider at CERN, has joined the search. By colliding protons at near light speeds, the LHC can recreate the conditions of the early universe, potentially producing dark matter particles in the process. If such particles were created in a collision, they would escape detection, carrying away energy and momentum. Detectors like ATLAS and CMS would record an apparent imbalance, missing energy that cannot be accounted for by known particles. Despite years of experiments, no conclusive evidence for dark matter particles has yet been found. But the search continues, expanding to higher energies and more precise measurements. The absence of detection does not mean failure. Each experiment, each null result, reshapes our understanding. The lack of WIMP signals, for instance, has led scientists to explore new models. Some propose that dark matter could be made of lighter particles, like axions, hypothetical entities originally proposed to solve a different problem in particle physics, related to the strong nuclear force. Axions, if they exist, would be extremely light and interact even more weakly than WIMPs. They could collectively behave like a wave that fills the universe, subtly affecting electromagnetic fields. Experiments such as ADMX and HAYSTAC are designed to detect axions by using powerful magnetic fields and sensitive microwave cavities, searching for tiny signals as axions convert into photons. Other possibilities include sterile neutrinos, a hypothetical type of neutrino that does not interact through the weak force, or even primordial black holes, small black holes formed in the early universe that could collectively account for dark matter. Each hypothesis demands its own kind of experiment and its own line of evidence. The challenge is immense. Dark matter interacts so weakly that even if trillions of particles pass through your body each second, they leave no trace. Detecting one requires enormous patience, exquisite precision, and often years of data collection. Yet scientists persist because the stakes are so high. Discovering the nature of dark matter would not only solve one of cosmology's greatest mysteries but also open a new frontier in physics. It would reveal an entire sector of the universe that has been hidden until now, a dark sector, governed by forces and particles that we have never seen. Some theories propose that dark matter could be part of a larger hidden symmetry, connected to new forces that interact only faintly with ordinary matter. Others suggest that dark matter might have self-interactions, that dark matter particles can collide and scatter with each other in ways that influence the structure of galaxies. Such interactions could help explain certain astronomical observations, like the cores of dwarf galaxies being less dense than predicted by simple cold dark matter models. In this way, the search for dark matter is not just a search for particles, it is a search for deeper laws of nature. Every experiment probes the boundaries of known physics, testing whether gravity, quantum mechanics, and particle theory can be unified into a more complete picture of the cosmos. As technology advances, new methods are being developed. Ultra-sensitive detectors cooled to temperatures near absolute zero, quantum sensors capable of measuring minute forces, and space-based observatories designed to map gravitational effects across the universe are all part of the next generation of exploration. The search has also moved beyond Earth. Instruments like the Alpha Magnetic Spectrometer aboard the International Space Station analyze cosmic rays, searching for excess particles that might result from dark matter interactions. Meanwhile, Future telescopes like the Vera C. Rubin Observatory and the Euclid mission aim to map the distribution of dark matter across the cosmos with unprecedented accuracy, using gravitational lensing and galaxy surveys to reveal how it shapes space-time. Each new piece of data brings us closer to understanding what dark matter is made of, or at least what it is not. With every refinement, the possibilities narrow and the mystery deepens. The search has also forced scientists to question whether our theories of gravity might need modification. Some alternative models, such as modified Newtonian dynamics and its relativistic extensions, attempt to explain galactic rotation curves without invoking unseen matter. However, these theories struggle to account for the full range of evidence, especially the gravitational lensing and cosmic microwave background data that point clearly to the existence of additional mass. Most physicists agree that dark matter, rather than modified gravity, remains the most consistent and comprehensive explanation. Still, exploring alternative ideas ensures that no possibility is ignored. The search for truth demands that every assumption be tested, every model examined. Deep beneath mountains, inside cryogenic chambers, and across the far reaches of space, humanity continues its quiet quest to find the unseen. Generations of scientists have built upon each other's work, refining instruments, analyzing data, and pushing the boundaries of sensitivity. Even in the absence of a signal, their work has transformed our understanding of the universe. Each attempt, each experiment, adds a new layer to the story. It is a story of persistence and humility, of searching for what may never be visible to the human eye. Yet it is also a story of hope. The hope that, one day, a faint signal will emerge from the noise, and the invisible will finally reveal itself. When that moment comes, it will be one of the most profound discoveries in the history of science. It will show that our universe contains far more than we ever imagined, that our understanding of nature's laws was only the beginning. It will open a window into the dark sector of reality, connecting the cosmic and the quantum in a way never before seen. Until then, the search continues. Underground detectors watch in silence, waiting for the rarest of collisions. Space telescopes scan the heavens for subtle traces of annihilation. Supercomputers simulate the universe, testing every possible variation. Each effort is a small step toward a greater understanding, an attempt to glimpse the hidden half of the cosmos. The universe holds its secrets patiently. Dark matter has remained unseen for billions of years, shaping galaxies, bending light, and guiding the evolution of space itself. Humanity's efforts to uncover it are young by comparison, only a few decades old. But the pursuit will continue, driven by curiosity and the unyielding desire to know what lies beyond the visible. The search for dark matter is not only a scientific endeavor, it is a philosophical one. It forces us to confront the limits of perception, to acknowledge that most of reality is hidden from our senses. It teaches us that light reveals only a fraction of what exists, and that the universe's true essence may be forever cloaked in shadow. And yet, even in that shadow, we continue to seek understanding. We build instruments to listen for whispers in the dark. We send telescopes into space to trace invisible threads of gravity. We write equations to describe what we cannot yet touch. Each act is an expression of faith. Faith in science, in curiosity, in the idea that the universe can be known, even in its deepest mysteries. Perhaps one day, a particle will strike a detector, a signal will rise above the background, and we will finally see what has eluded us for so long. Perhaps the answer will come from an unexpected direction, a new theory, a new particle, a new way of seeing. Whatever form it takes, the discovery of dark matter will mark a turning point in our understanding of the universe. It will complete the picture of cosmic composition and illuminate a hidden world that has been with us from the beginning. Until that day, the search goes on, quietly, persistently, beneath mountains and among stars. The detectors remain vigilant, the scientists patient. The universe waits, its greatest secret still intact. The universe continues to expand, stretching space itself across unimaginable distances. Galaxies drift farther apart, and the light that travels between them grows fainter, red shifted into the long wavelengths of time. In this quiet cosmic unfolding, dark matter continues to play its silent role, guiding the evolution of everything that exists. Though invisible, it is the unseen architect of the cosmic web, and in its mysteries may lie the key to the universe's ultimate fate. Dark matter has shaped the universe since its earliest moments. Its gravity gathered primordial gas into the first galaxies, providing the invisible scaffolding upon which stars were born. Even now, as the universe ages, dark matter continues to dictate how cosmic structures grow and change. To understand its nature is to understand the story of creation itself, not just how the universe began, but how it will end. In the grand tapestry of cosmology, dark matter is woven together with another great enigma, dark energy. While dark matter pulls the universe together through gravity, dark energy drives it apart, accelerating its expansion. The two make up most of the cosmos, yet both remain unseen. The balance between their forces determines the ultimate destiny of all that exists. If dark matter were to behave differently over time, if its density or interactions changed even slightly, the universe's history would unfold in new and unexpected ways. Some cosmologists speculate that dark matter might decay, slowly transforming into lighter particles or radiation over trillions of years. If that were true, galaxies could eventually lose the gravitational glue that holds them together, fading into isolated islands of light adrift in expanding darkness. Others suggest that dark matter could be part of a larger, hidden sector of physics, a mirror universe filled with its own particles, forces, and even dark atoms. In this picture, dark matter might not be a single type of particle at all, but an entire hidden ecosystem that mirrors the visible one, interacting through forces that ordinary matter cannot feel. Such a discovery would revolutionize not only physics but our understanding of existence itself, revealing that reality is far richer and more complex than we ever imagined. As scientists study the universe's large-scale structure, the clustering of galaxies, the cosmic microwave background, the formation of filaments and voids, they are piecing together a precise map of dark matter's influence. These measurements suggest that dark matter behaves as a cold substance, moving slowly compared to the speed of light and forming dense halos around galaxies. But the exact properties remain unknown. Future missions, like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, aim to measure the shapes and distributions of billions of galaxies, tracing the subtle warping of light caused by dark matter's gravity. This cosmic cartography will help refine our models and test whether dark matter is truly cold or if it possesses more exotic properties, perhaps warm or self-interacting, influencing the fine structure of cosmic evolution. On Earth, the search continues in parallel. Each new generation of detectors is more sensitive than the last, pushing deeper into the realm of the almost undetectable. Scientists have learned to listen for signals so faint that they could easily be lost in the hum of the universe. Each year brings new data, new constraints, new ideas. The absence of discovery is not a void but a guide, narrowing the possibilities of what dark matter could be. In the quiet corridors of laboratories, surrounded by liquid xenon and cryogenic crystals, researchers work in near total silence. They are searching for something that has never been seen, something that may not even interact with them in any measurable way. Yet they persist, because the reward is immense. To find dark matter would be to glimpse a hidden layer of reality, to open a new chapter in the story of the cosmos. Beyond the technical challenges, the search for dark matter also represents something deeper about humanity, our enduring curiosity, our willingness to explore the unseen. We have always reached for what lies beyond the horizon, from the edges of maps to the edges of the universe. Dark matter is the modern frontier, the place where our knowledge meets the unknown. As we study it, we are also studying ourselves, our methods, our imagination, our ability to accept mystery without surrendering to it. The effort to understand dark matter is a reflection of the human spirit, one that thrives in the face of the impossible. Even if the search takes generations, even if the answer remains elusive, the journey itself reshapes our understanding. Each hypothesis tested, each experiment built, each new observation of the cosmos deepens our comprehension of the laws that govern reality. Dark matter may turn out to be something entirely unexpected, not a particle, but a manifestation of a deeper principle. Some physicists entertain the possibility that dark matter could arise from the geometry of space-time itself, from hidden dimensions or quantum fluctuations that extend beyond our perception. These ideas blur the line between physics and philosophy, between what is measurable and what is fundamental. If such possibilities prove true, they would transform not only cosmology but the nature of science itself. They would show that the universe's most profound truths may lie not in the particles we can detect, but in the structure of reality that defines detection itself. For now, the cosmos remains quiet. Dark matter continues its silent dance, shaping galaxies, guiding stars, bending light, and holding the universe together in its invisible embrace. From the smallest dwarf galaxies to the vast filaments that stretch across billions of light years, its gravity connects everything. We live within its web, sustained by a presence we cannot see. Every galaxy, every planet, every atom of our being is part of a structure defined by it. The visible universe, the glowing stars, the radiant nebulae, the shining galaxies, is just the surface, a luminous lace draped across a vast invisible framework. If we could see dark matter directly, the night sky would appear transformed. Instead of empty blackness between stars, we would witness a vast and intricate structure. Filaments glowing with ghostly light, clusters woven together by invisible threads of gravity, and great cosmic voids where matter is scarce. It would be a vision of breathtaking complexity, a reminder that what we see is only a fraction of what exists. As the universe continues to expand, galaxies will move farther apart. Over trillions of years, stars will exhaust their fuel, and light will fade. Yet dark matter will remain, its gravity persisting long after the last star has died. Even in the deep future, when the universe grows cold and dark, dark matter will continue to shape what little remains. Some cosmologists imagine that in that distant epoch, when time stretches beyond human comprehension, dark matter may decay or transform, slowly releasing its energy back into the cosmos. Others believe it will endure indefinitely, a permanent and silent witness to the passage of eternity. Either way, dark matter will continue to define the universe's structure long after the light has gone out. It is the foundation of cosmic architecture, the unseen pattern upon which all else is built. For those who study it, dark matter is more than a scientific mystery. It is a poetic reminder of how little we truly know. The more we learn, the more questions arise. Each discovery opens new horizons of ignorance, deeper and more beautiful than the last. It is humbling to realize that most of the universe is invisible, that our existence depends on something we cannot yet explain. But it is also comforting, in a way, to know that there are still mysteries waiting in the dark, that the cosmos still holds secrets for us to uncover. Our ancestors once looked at the stars and saw gods, stories, and symbols. Today, we look and see galaxies, quasars, and cosmic radiation. Yet the feeling is the same, a quiet awe at the vastness of existence, a sense of belonging to something infinite. Dark matter invites us to keep looking, to keep questioning, to never assume we've reached the end of understanding. It reminds us that even in silence, the universe speaks. It speaks through the motion of galaxies, through the bending of light, through the faint imprints left in the afterglow of the Big Bang. When we listen carefully, we can almost hear it, the whisper of the invisible, the subtle pull of gravity shaping all that is. Perhaps the true revelation of dark matter is not just what it is, but what it teaches us about knowledge itself. That even in an age of advanced technology and deep understanding, the universe can still surprise us. That mystery is not the enemy of science but its greatest companion. As the night deepens and stars drift across the sky, the thought of dark matter brings both wonder and peace. Somewhere, beyond the reach of our eyes, the invisible mass of the cosmos continues its ancient work, holding everything together with quiet strength. It is everywhere, yet nowhere to be seen. It flows through galaxies, through space, through time, unseen but essential. The universe rests upon it, balanced upon its unseen framework like light upon shadow. And so, as we gaze into the darkness, we are not looking into emptiness. We are looking into the heart of existence itself, a realm of unseen forces, hidden symmetries, and eternal quiet. Dark matter is not merely a problem to be solved. It is a reminder of the depth of the unknown, a reflection of the infinite complexity that underlies the simplicity of night. The search continues, as it always will. Scientists will keep watching, listening, measuring, and imagining. They will build new instruments, explore new ideas, and push beyond every known frontier. Perhaps one day, a faint signal will reveal itself, a whisper from the dark, the first confirmation that we have finally found what we have long sought. When that day comes, the story of the universe will be rewritten. But until then, the mystery remains, silent, vast, and beautiful. The cosmos rests in balance between what we can see and what we cannot. The stars may shine, but it is the darkness between them that gives the light its meaning. And within that darkness, unseen and eternal, the quiet presence of dark matter endures, the invisible heart of the universe. The universe drifts in quiet balance. Long after the first light burst from the newborn cosmos, the great machinery of space continues to move in slow, deliberate rhythm. Galaxies spin, stars ignite and fade, and dark matter, unseen and untouchable, flows around them like an ancient tide. The search to understand it has taken humanity to the limits of knowledge. Yet the deeper we look, the more we are reminded of the immensity of the unknown. Now, as the night deepens and the questions soften into wonder, we can let the mind wander across the endless distance, tracing the patterns dark matter has drawn through time. Imagine the first moments after the Big Bang, when all that would ever exist was compressed into a single, blinding point. Out of that instant came matter, radiation, and the laws that govern them. Among the newborn particles was a kind of matter that did not shine, silent, weighty, invisible. It has been there from the beginning, guiding the universe into form. Without it, the cosmos would be a very different place. Stars would not have gathered, galaxies would not have taken shape, and the vast filaments that connect everything would never have formed. Dark matter is the quiet architect of existence, the invisible hand that sculpted the universe into something capable of harboring light, life, and thought. As we look back across cosmic history, we see not only a record of light but a record of gravity, the pull of something unseen. It is through this subtle influence that we know dark matter is there. We feel its presence in the rotation of galaxies, in the motion of clusters, in the bending of light across the emptiness of space. It has never spoken, never revealed itself directly, and yet it has shaped every corner of the visible universe. Humanity's journey to understand this mystery has spanned generations. From the early astronomers who mapped the motions of stars to the physicists who probe the smallest building blocks of reality, each step has brought us closer to the threshold of comprehension. We have built instruments to see deeper, to listen for whispers in the dark, to measure what cannot be seen. And still, the dark remains silent. But silence is not emptiness. It is a language of its own, patient, steady, profound. It reminds us that the universe does not owe us answers, it invites us to seek them. The search for dark matter, at its heart, is an act of faith in the power of curiosity. It is a testament to our belief that understanding is possible, even when the subject lies beyond sight. The night sky above is filled with light that has traveled billions of years to reach us. Each photon carries the memory of its origin, a distant star, a supernova, a galaxy born in the early universe. Between those points of light lies a far greater expanse of darkness. But that darkness is not empty. It is full of the invisible structure that holds everything together. To close your eyes and imagine that hidden world is to drift beyond the boundaries of perception. It is to feel the quiet hum of gravity beneath the fabric of space, the soft tension that binds galaxies in their slow, eternal spin. In the stillness, one can sense the truth that the visible is only a fraction of what is real. The rest, the vast majority, lies beyond the reach of light. And yet, that unseen realm is what gives meaning to the stars. It is strange to think that the cosmos we can see is only the surface of a much deeper reality. The light of stars, the color of nebulae, the brilliance of galaxies, all are mere reflections of the underlying structure that dark matter has woven through space. We live within its web, move through its currents, and rest upon its invisible foundation. In the quiet of night, this realization can be comforting. It reminds us that even in darkness there is order, that what we cannot see still supports us. The universe is not chaos, it is harmony written in a language of gravity and time. For all our sophistication, for all the machines we have built and the equations we have derived, the mystery remains. Perhaps that is how it must be. Every age of discovery ends with a new horizon. Every explanation opens another question. The search for dark matter is not a puzzle with a single answer. It is a window into the boundless nature of knowledge itself. The more we learn about the cosmos, the clearer it becomes that our understanding is only beginning. The universe is not a solved equation. It is a living story, unfolding in every direction. Each galaxy is a chapter, each particle a word, each human question a spark of meaning flickering against the dark. In time, we may find the particle that explains it all. Or we may discover that the answer is something we have never imagined, a new form of matter, a new law of physics, a new way of seeing. But even if we never capture it, the pursuit itself has value. To search is to participate in the universe's own curiosity, the impulse that drives stars to form and life to awaken. The act of wondering is, in itself, an expression of the cosmos becoming conscious of its own structure. We are part of the very universe we seek to understand, a brief, luminous awareness emerging from a sea of dark matter and energy. In that sense, the mystery of dark matter is not separate from us. It flows through us, as surely as it flows through galaxies and clusters, binding the visible and the invisible in a single cosmic design. Let your thoughts wander across the deep night of space. Picture yourself floating among the galaxies, surrounded by silence. The stars drift slowly past, each one a point of ancient light. Between them, the darkness stretches forever, soft and endless. In that darkness lies the true substance of the universe, quiet, patient, infinite. There is no boundary, no edge, no center. Only an ocean of gravity, of particles too faint to see, of space expanding into eternity. And somewhere within that ocean, a small world turns, bathed in the light of a nearby star. On that world, we look up and wonder. The search for dark matter connects us to something vast and timeless. It is a reminder that we are not apart from the cosmos but expressions of it. The atoms that make us were once the dust of stars, shaped by the same forces that dark matter commands. Our curiosity, our science, our art, all are reflections of the universe's desire to know itself. To lie beneath the stars and listen to the quiet is to join in that cosmic rhythm. The heartbeat of the universe is slow, measured in the turning of galaxies, in the fading of starlight, in the drift of dark matter across time. Our lives are brief, but they are part of that rhythm. Dark matter is not simply a mystery to be solved, it is a mirror. It shows us that reality extends far beyond our senses, that what we see is not all there is. It invites humility, a gentle recognition that knowledge is infinite, and we are only beginning to awaken to its depth. As you listen, let that thought become lighter, slower, softer. The universe is vast, but it is also kind. It holds us, every atom, every heartbeat, every breath, within its gravitational embrace. There is no need to rush to an answer. The mystery is enough. The seeking is enough. In the stillness of night, surrounded by the unseen, we are at home. The night stretches on, and the stars wheel slowly overhead. The galaxies continue their eternal drift through the vastness, each one carrying billions of suns, each sun encircled by the quiet gravity of unseen matter. The same invisible substance that shapes the great cosmic web also surrounds us here, moving silently through every room, every mountain, every ocean. We live inside its presence, unaware, yet dependent upon it for the very structure of the universe. It is humbling to realize that the most dominant form of matter in existence passes through us at every moment, unnoticed. Dark matter does not collide with us, does not glow, does not whisper, it simply is. It shares space with everything we know, and yet we never touch it. Its patience is infinite, its influence immeasurable. The galaxies dance to its rhythm, though it makes no sound. When scientists measure the shape of the universe, they find harmony in its design. The luminous filaments of galaxies stretch like veins through the body of creation, each strand held in place by dark matter's invisible gravity. Between those filaments lie enormous voids, regions so empty they seem to defy comprehension. Yet even there, dark matter lingers, thin as a ghost, stretching the fabric of space. The pattern is elegant, almost biological. The cosmic web resembles the neural network of a brain, the tendrils of a living organism. Perhaps, in some abstract sense, the universe itself is alive, not conscious as we are, but self-organizing, creative, evolving. If so, dark matter may be its hidden skeleton, the framework on which all visible beauty is hung. Each discovery we make about it brings us closer to understanding not just the cosmos, but our own place within it. The same mathematical laws that govern the clustering of galaxies also describe the motion of atoms within our cells. The universe is consistent. It speaks one language, written across every scale of existence. When we study dark matter, we are listening to that universal grammar, the deep syntax of being itself. In laboratories buried beneath mountains and oceans, detectors wait in perfect silence for the faintest sign of dark matter. They are vast instruments, yet their purpose is almost spiritual, to catch a whisper from the unseen. Perhaps one day a single particle will reveal itself, a spark in the dark that confirms the theory. Or perhaps it will remain forever beyond our reach, a permanent reminder of humility. But whether we find it or not, the act of looking has already changed us. Each generation that peers deeper into the unknown learns to see farther, not just with the eye, but with the imagination. The search for dark matter is, in its essence, a meditation on patience. The universe does not hurry, and neither should we. In its slowness lies eternity, in its silence, meaning. If we could stand outside the universe and watch it unfold, we might see the slow blossoming of galaxies as flowers of light, blooming within a garden of darkness. Dark matter would be the soil, unseen but necessary, the foundation from which everything grows. Over cosmic time, it has guided the paths of galaxies, ensured the birth of stars, and sustained the possibility of life. And here, on one small planet, in one small corner of one galaxy, that life has begun to wonder why. It is a remarkable symmetry, the invisible shaping the visible, and the visible becoming aware of the invisible. That is the quiet miracle of consciousness, the universe observing itself, pondering its own shadow. As you breathe, Imagine that you are breathing with the cosmos itself. Each inhalation a tide of creation, each exhalation a release into the dark. The atoms in your body were once scattered through the early universe, carried along currents of dark matter that guided them together into stars, and then, after eons, into you. You are not separate from the universe. You are one of its expressions, a fleeting moment of awareness within an ocean of time. There is peace in knowing that everything follows a natural order. Stars are born, they burn, they fade, and their remnants become the seeds of new stars. Galaxies merge, black holes sing at their cores, and the universe continues to expand, cooled by the passage of time. Through it all, dark matter remains constant, steady, unchanging, eternal. It is the background pulse beneath the symphony of existence. Eventually, the stars themselves will die, and the galaxies will grow dim. The light will fade, leaving behind only the faint glow of the last embers. Yet even then, dark matter will endure, holding space together long after the luminous universe has gone silent. In that final stillness, the legacy of dark matter will remain, the structure it built, the harmony it sustained, the possibility it gave for beauty and for thought. Perhaps, in that far future, something new will arise, a new kind of physics, a new expression of matter and energy. The universe may find new ways to create, to change, to become. Or it may simply rest, suspended in quiet equilibrium. Whatever its fate, dark matter will have been its constant companion, the unseen thread woven through all of history. For us, here and now, that story is enough. It tells us that the universe is vast, that our lives are brief, and yet that we are connected to the whole by invisible bonds. The same gravity that binds galaxies also holds us gently to our world. The same mystery that hides in the darkness of space also stirs within our minds. As the voice of the documentary grows softer, imagine the cosmos dimming around you. The stars fade into mist, the galaxies drift away, and what remains is only the deep pulse of space. Quiet, steady, eternal. The sound of your own breath becomes part of that rhythm. You are floating, weightless, in the calm sea of dark matter. There is no boundary between you and the universe. You are made of it, sustained by it, surrounded by it. Every heartbeat, every thought, every dream is an echo of that original creation. The atoms in your blood once danced in the hearts of stars. The gravity that holds you was born in the same explosion that made the galaxies. The mystery of dark matter is not something to be solved tonight. It is something to rest within, to let it wash over you like a tide of quiet understanding. You do not need to see it to know that it is there. You feel it, in the pull of the earth, in the stillness between moments, in the infinite calm of the night sky. Let the darkness become gentle now. Let it hold you, the way it holds the stars. The universe is vast, but it is also tender. It has carried everything that has ever been and everything that will ever be, through the slow drift of time. You are part of that journey, a note in the endless song. As the last light fades, the story closes, but the universe continues. Dark matter keeps its silent vigil, and we, for a brief moment, have seen its shadow. In that shadow, we find peace. Rest now, within the quiet gravity of the cosmos. The stars will keep their watch. The galaxies will continue their slow dance. And dark matter, timeless, invisible, eternal, will cradle the universe in its gentle embrace, forever.